Now it's time to have some fun. We can apply our blackbody theory to the situation when the blackbody has a leak. That seems like an obscure situation, but you'll find out that it has huge consequences to our understanding of modern science. Let's get started. Once again, we will use our light as particles model with the photons bouncing around inside the container. This model lets our human brains visualize what's happening. Just keep in mind that the model also leads to paradoxes and incorrect predictions. A more accurate model uses the energy in the field instead of counting photons. For our situation, both models produce the same mathematical results. So, what if there's a hole in the container? How much radiation will exit the hole per second? In 1880, physicists made measurements to answer the question experimentally. They used detectors that measured the total radiation at all frequencies. The first result was that the amount is proportional to the area of the hole in the container. That's almost common sense. The hard question was, how did it vary with the temperature of the container? They plotted their data like this, with detector response on the y-axis and temperature on the x-axis. The red dots show their measurements. Then they tried to fit the data to various curves. The data didn't fit a t-squared curve. It didn't fit a t-cubed curve. There was a very good match with a t to the fourth curve. So they developed an empirical formula for the total amount of radiation emerging from a hole of area A, and it looked like this. The energy emerging is equal to the area of the hole times a constant called sigma times the temperature to the fourth power. The new proportionality constant, sigma, was named Stefan Boltzmann's constant. The formula fit the data when the constant was adjusted to 5.67 times 10 to the minus 8th watts per square meter per degree to the fourth. This is Stefan Boltzmann's law, as originally formulated in 1880 from the best fit to the experimental data. It had no theoretical explanation. Theoretical physicists now had the task of explaining the law in terms of basic principles. The theoretical explanation came as an immediate result of Planck's blackbody theory. Here's how the logic went. First, remember Planck's equation for the energy in the container at a particular frequency. We derived that in previous videos. To get the total energy in the whole container, just add up the energy from every frequency. The integral is not easy, but it's doable. Divide that total energy by the volume of the container, and you get the energy density, which is what we will need shortly. Notice that the energy density formula has a t to the fourth in it. We have a clue that we might be on the right track. Now imagine a tiny volume inside the container with volume dV. We will represent it as a red dot, and it can be anywhere inside the container. The energy in the little volume is U times dV. If you draw a sphere around the little volume, then the energy flowing out of the little volume has an equal chance of hitting the sphere at any point on the sphere. You can visualize this as photon particles flowing from the little red dot. The photons have an equal chance of hitting anywhere on the whole sphere, whose surface area is 4 pi r squared. If there's a hole in the sphere of area A, then the probability of a photon going through the hole is A divided by 4 pi r squared. That's the physics of the situation. To get the total energy flowing out of a real hole in the container, you have to sum all the contributions from all the little volumes inside the container. It's a good math problem, but too tedious for video. I'm just going to skip to the answer. After all the integrals are done, you get the energy flowing out is equal to the area of the hole times the speed of light times 1/4 the energy density. Replacing U with our energy density formula gives the result that made Max Planck a happy kid. The energy exiting the hole per second is the area of the hole times a constant times the temperature to the 4th power. Max Planck had derived a T to the 4th law from his blackbody theory. Ta-da! Now he had a formula for the Stefan Boltzmann constant. Since the Stefan Boltzmann constant had been previously measured, Max Planck could solve for the value of the Boltzmann constant, which had not been measured, even by Dr. Boltzmann himself. He got that the Boltzmann constant was 1.38 times 10 to the minus 23rd in MKS units. Thus, in 1900, Planck's blackbody theory provided the best value for the Boltzmann's constant, which is a key to many more predictions. Now remember that chemists in the 1800s had measured the universal gas constant, knowing only moles and not knowing the number of molecules per mole. The number of molecules per mole is called Avogadro's number, and it can be calculated once you know the Boltzmann's constant. A high school student can show you the formula. And for the first time in history, Planck knew that the number of molecules per mole is 6.02 times 10 to the 23rd. Thus, measuring blackbody radiation allowed scientists to calculate the number of atoms in a mole. Are you surprised? You should be. After Avogadro's number and the Boltzmann's constant came a cascade of results. To begin with, chemists could now measure the size of atoms because they could measure the weight of solids and knew how many atoms were in the solid. Similarly, by measuring the number of atoms deposited during electroplating and the amount of current that flowed, they could get a value for the charge on an electron. Knowing the charge, they could calculate the mass of the electron, because the charge-to-mass ratio had been determined from Thomson's electron beam experiments. So just look at all that was learned from studying blackbody radiation. It proved to be the key that unlocked a giant puzzle. Today, most people depend on modern science, and millions of kids are taught atomic theory in school. They may not know where the theory came from, but now you know. It all started with blackbody radiation.